Hey, Martians. So, as you may have gathered from some of the topics that I've posted, I really like things that have to do with geometry in space and how the different orientations and movements of objects create different astrophysical phenomenon, or astronomical phenomenon, I guess I should say. So, there's an important day coming up on January 20th on Mars. I thought I'd do a little bit of explanation on it. It's probably going to be a 2 or 3 part video. So, as the Earth goes around the Sun, the tilt of its axis causes the seasons. And one of the consequences of the seasons is that the length of day changes. The length of daylight that you have changes. The day is still 24 hours, but the amount of light that you have is, changes depending on how you're oriented with respect to the sun. But there's another effect that goes on. It's much more subtle, but it has a great deal of implication for timekeeping. In this little animation here, the Earth is going around the sun, and it's a nice little... And you can see that it's moving at the same speed all the time. But this isn't the way it actually works. In reality, the orbit of Earth and Mars and essentially every planet is at least slightly elliptical. One consequence of an elliptical orbit is that you go faster when you're close to the sun and slower when you're far away from the sun. So what this means is that on any given day, if you were in a circular orbit, you go 24 hours around, and then the sun is at the same place in the sky. But the Earth is also moving along its orbit as this happens, and so that noon position, that zenith position, shifts a little bit because the Earth is moving slightly faster or slightly slower than it would if its orbit were circular. The effect that this has is it actually changes the length of time between successive noon events. So there's this equation called the equation of time, and it tells you by how many minutes the sun's apparent position is deviating from true noon, when the sun is at its true zenith point. And so on Earth, this varies from about 15 minutes to about minus 16 or 17 minutes. And it varies over the course of the year. This is, 0 days from January 1st to 365 days. And so it varies a little bit, and then it comes right back and it loops around again. So this is the consequence of Earth's eccentricity. If you take this and you just kind of fold it back on itself, it makes this little figure 8 shape, where the Tropic of Cancer is here, and the Tropic of Capricorn is here, and as the sun moves along, its number of minutes away from the 0 point changes. And this figure, if you turn it on its side, make a little figure 8 like that, it is called the Analemma. You've probably seen it printed on globes before, and it's a way to visualize the position of the sun if you looked at it at the exactly 24 hours apart every single day. There's this great animation here. It may not come through very well on your view, but it shows how, as the Earth moves along its elliptical orbit, the sun's position at its zenith actually changes over the course of the year. So if you took an image at true noon, which is when the sun is at its zenith, the position of the sun would be different each day because the orbit is slightly faster or slower. And in reality, you can take year-long sort of quasi-time-lapse photographs at true noon and see the position of the sun make this lovely figure 8 pattern, the Analemma. Well, on Mars, we also have an elliptical orbit, but because the orientation of the orbit is different, and where daylight or where the perihelion is with respect to the axial tilt direction, results in a different shape. The equation of time looks different, and the Analemma looks different. It's kind of this teardrop shape. And it just so happens that January 20th is a day when the equation of time reaches its maximum, and we're at a maximum deviation of about 51 minutes from the true, rotational day, which on Mars is longer than Earth's day. It's not 24 hours, it's 24 hours, 39 minutes, and some seconds. But then the actual length of day will deviate by up to 51 minutes there and down to 40 minutes there. So it's a larger deviation than we have on Earth, and it results in an analemma which looks very different. So January 20th is the day when we hit that peak. It's doesn't really matter for almost any purpose except for timekeeping, but I just think it's really cool. So, there.